In this video, we will learn to predict the response of the system given a reversible reaction and a stress is applied to a system at equilibrium. 2. Infer the properties of underlying reversible reaction given an observed reaction of a system to a stress. For example, given the response to a change in temperature, infer whether the reaction is endo or exothermic. Let us say we have a reaction in which molecule A is in dynamic equilibrium with molecule B. At equilibrium, we know that the concentration of A and concentration of B remains constant over time, and the rate of forward reaction is equal to the rate of reverse reaction. Recall that the rate of forward reaction depends on the concentration of A, and the rate of the reverse reaction depends on the concentration of B. At this point, let us say I add more A to the reaction mixture. What happens to the equilibrium? Think about it. When I add more A to the reaction mixture, the concentration of A in the reaction mixture increases. Consequently, the rate of forward reaction increases as well. So, at the moment we add more A to the reaction mixture, the rate of the reverse reaction was the same as before, but the rate of the forward reaction increased. That is, the system at that point is no longer at equilibrium. Let me represent the addition of A on concentration of reactant and product versus time graph. As you can see, at certain point after the reaction reached equilibrium, the concentration of A suddenly increased. Because the rate of forward reaction is greater than the rate of the reverse reaction, the concentration of A decreases over time and the concentration of B increases over time. In other words, the reaction moves towards products or shifts right. As the concentration of A decreases, the forward rate decreases, and as the concentration of B increases, the reverse rate increases. After a certain time t, the forward rate again becomes exactly equal to the reverse rate. In other words, the system reaches a new equilibrium. So, we took a reaction that is at equilibrium and added more reactant to it. At that moment, the reaction is no longer at equilibrium. Over time, the concentration of the reactant decreased and the system reached equilibrium again. This behavior of an equilibrium reaction is defined by Le Chatelier principle. According to the Le Chatelier principle, when an equilibrium reaction is stressed, the chemical reaction is no longer at equilibrium, and the reaction starts to move back towards equilibrium in such a way that it relieves or decreases or counteracts the added stress. In the above example, the stress is increase in the concentration of A, and the response of the system is to decrease the concentration of A by shifting the reaction to the right. The take-home message here is the stress applied on the equilibrium and the response of the equilibrium are always in opposite directions.